In this video lecture, I will introduce Inference for the Lasso and we'll take a first look at how we could go on and solve the problem of post-selection inference. As we discussed last week, we need methods that allow you to have uniform convergence to limit distributions in order to have reliable inference. If not, then the properties of the method will depend on the actual values of the parameters, which we don't know. And we need to avoid such reliance on these parameter values, for instance through beta min conditions, which tell you that all parameters need to be large enough, far enough away from zero, to avoid the problems of uniform inference. Now, methods which do not rely on such assumptions are called honest inference methods, because they do not rely on misleading arguments and assumptions that you could never verify. Now, this has been a very active field over the last, say, 5 to 10 years, and many methods have been developed and actually are still being developed. Now, before we go into detail about those methods in separate lectures, let's very briefly look at two methods which might not be totally honest, but at least are an improvement over standard oracle inference. And these were basically the first steps in going towards honest inference. So while these methods do not really solve all the problems that we need to solve, at least they should be preferred over oracle inference. They are generally applicable, and they do account to some degree for the fact that we have this model uncertainty and first select the model and then do inference in a second step. So one of these methods is sample splitting. Sample splitting is discussed in the book SHD, and it deals with the basic problem that post-selection inference has, where we say, well, we first use the data to select a model, and then again we use the same data to do inference, which is this data snooping idea that you want to avoid. Well, sample splitting is the most basic way to avoid that. Essentially, you split your data in two parts. You split them in a half. You use one half to select your model on, and you use the second half to do inference. Now, if these data are actually independent, then of course your two samples will become independent. And so you can genuinely treat the data after having selected the model on another part as a new set of data, which does not suffer from the fact that you already used them to find the optimal model. Now, obviously, given that there is a multitude of ways in which you can split your data, you would not want to do that once, but instead you would want to do that many times. So we basically do a bunch of splits, repeat many times, and then randomize actually which data end up in which part. Now, there are some issues with this method still. First, we need to be able to create independent samples, so that, for instance, for time series, this would be much more complicated. It's still possible, but it's more complicated. Well, and then the bigger disadvantages are, first, you get a lot less power of your tests, and means also you get longer confidence intervals, because you're basing everything on only half of the data. So first of all, the model selection is hurt. You get there's more uncertainty in the selection, and then there's also more uncertainty in the inference. So in that sense, you clearly sacrifice a lot in doing sample splitting. Now, we'll come back to that in one of the other methods that we'll discuss later on how to do that in a better way. And of course, the second thing, and that is of course related to the honesty of the method, convergence remains pointwise. So you still need the beta min condition in order to do uniformly valid inference. The other method is the bootstrap. Well, there are several bootstrap methods, but let's focus here on the most basic one, proposed by Chatterjee and Lahiri. And they just say, well, what we do is simply a pairs bootstrap where we draw with replacement from the original sample, we draw a new sample. So we keep y and x together and draw with replacement from that vector. Well, and then you can just calculate your betas using the lasso or adaptive lasso or whatever you're using. Repeat this capital B times, you get a collection of values of the estimator on the bootstrap data, you subtract the true bootstrap parameter, and then you can use that for inference on beta. Now here's a thing that we need to take care. If we do the adaptive lasso, we just do as standard. We treat our estimator on the original data as the true bootstrap parameter. But for the lasso, we need to modify that. And we need to put a threshold, and we only put the estimator as the true value if it's large enough, if it's far enough away from 0. So we create some sequence Cn such that this is going to be, we can put a threshold on that. And that is because there are too many small coefficients estimated by the lasso, and we need to get away from that. This provides, of course, more accuracy in smaller samples, and you do replicate the whole model selection process within the bootstrap. So it does take that into account, but still it is not uniform, so it's still not really honest inference. So to go to honest inference, we will do that now in the methods that will be discussed in the next lectures.